Thank you all for coming today. It's Saturday, it's before noon, so really appreciate the audience. My name is Michal Ptaszek, and I'm a software architect at Riot Games. I'm today to talk about Riot Messaging Service, or RMS in short. So before we kick off, just for my observation, how many of you have ever heard or played League of Legends? Holy crap. Okay. That's amazing. Cool. Riot Games is a developer and publisher of League of Legends. More about the game for those who never heard of it in a second. But as a company, our main focus is really on the player experience. We use it as a razor for making any decisions, regardless of they are product or technology oriented. It helps us tremendously that we are all gamers here. Like, we really play games, enjoy them, and we can empathize with other players. Our mission is that we aspire to be the most player-focused game company in the world. So what is League of Legends? League of Legends, we launched the game in 2009, and since then we've grown the player base to some pretty big numbers, and more about the numbers in a second. League of Legends is a team-based game in a genre called MOBA, which is a multiplayer online battle arena, where two teams compete to control a map and achieve objectives. Each player of these teams controls one champion, and typically teams consist of 5 players. The entire game is placed in a modern fantasy world. To give you some more context around the scale and types of problems we were trying to solve when architecting Riot Messaging Service, here are some numbers we released in September 2016 regarding popularity of League of Legends. So we are super lucky to have over 100 million players enjoying the game monthly, and out of which over 27 million players play League daily. If you check our systems at any given time of a day, we can see at least 7.5 million players connected to our servers. So all of these numbers heavily influenced decisions we've made when building RMS. So now let's jump to a quick overview of what we're going to cover today. I would like to start with a very high-level design of Riot Messaging Service. Then I would like to follow up with the implementation, how we got there, and what were the architectural decisions behind RMS, as well as what were the key lessons learned for us when we created it, and also what are the plans for the future for the service. Okay, let's start. So before we jump directly into design of RMS, let's kick off with describing why we even wanted to build RMS in the first place. In the old way, when we started building League, the old way of handling player-to-server communication for the out-of-game events used persistent TCP connections using LCDS RTMP protocol. That's a proprietary binary protocol introduced by Adobe. Overall, it was designed to handle media, but we decided that it's a great fit for game traffic, or not even game, but out of the game traffic as well. And it turned out that the protocol really was having really big issues with security. The way we built the platform as a monolith prevented us from growing it fast, deploying and transitioning into the microservice world with very fast iteration loops. We also suffered from pretty significant scalability issues. A single instance, a single server holding all player connections could only handle around 30,000 players. Given the scale we were operating at, building out the platform for hundreds of millions of players was a huge challenge. And as we were building more and more features for League and also other products in R&D, we realized we cannot really replicate the same pattern, and we needed something better. And that's how we created RMS. RMS or Riot Messaging Service, is a backend service, something we deploy on the server side. It provides asynchronous messages capabilities, notifications that are sent using the fire and forget semantics from services, from backend services to connected players. So that's the way for the backend microservices to somehow deliver either notifications or payloads to clients, for example, League client. Today, RMS has been adopted by over 20 different products and features at Riot and is used every day by all League players around the world. To give you an example of what features use RMS, it's clubs, which are player-organized and controlled social groups. It's missions, which are challenges for the players with rewards. And honor, which is a system that encourages positive behavior among the community. To better illustrate how RMS works, let's use mobile push notification analogy. In the beginning, let's imagine that we have someone sending us an email. The email hits our email server, and email server stores it in some sort of a database. The interesting thing is that that email server, because everyone now uses smartphones, figures out that, okay, that recipient probably has a phone and would like to be notified that he has an incoming email. In that case, that email server sends a request to the push notification service, informing it that, hey, you've got an email. But because your incoming email might be pretty big, it might also have attachments, you don't necessarily want to receive them as push notifications. As a matter of fact, the push notification servers have very strict limits when it comes to size. So what happens is that the push notification service actually receives only a very high-level digest of what the email is, which is the subject of the email, sender, and maybe few first paragraphs of text. It sends a push notification to your phone buzzes and displays a toast on your home screen. And then, some time later, you're going to go into your email app, open it up, and download the original email, including attachments, all the text, and all the context around the email. But instead of going to the push notification service, you're going to go to your original email server. RMS works in a very similar way, but instead of the mobile phones, we have desktop clients, or League of Legends clients, and instead of the push notification service, we have RMS. Let's see how it works with League of Legends example as clubs. As mentioned earlier, clubs are player-created, organized, controlled social groups. Each club can be described using several properties. For example, the club name, club roster, which is a list of members with their ranks, message of the day, and so on. First of all, whenever you start League of Legends, you launch and authenticate with our servers. As a result, you're going to get a signed JWT token claiming who you are, so that you can prove with other servers that you are in fact you. As soon as authentication is done, RMS requires clients to establish a persistent TCP connection using WebSocket protocol as a transport in order to receive any incoming notifications. This is an example of WebSocket URI. The aforementioned token we got from the authentication service is highlighted in red here. So we pass that to RMS, and RMS is essentially authenticating, validating the token, and letting you in. As one of the claims encoded inside of the token, there is a field called subject, which we interpret as player ID. Player ID is a standard way to identify players in our ecosystem and is used by all internal services at Riot. It's also globally unique and immutable. Internally, we called this player ID PUID as Player Universal Unique ID. And as soon as the connection is established, League client will go to the club service to fetch the latest state. And by state, I mean list of clubs that this player is a member of, and for each of those clubs, all the details about the clubs. And then clubs are ready to go. You have chat, you have a list of members, and you can start using them. What happens when there is an invite incoming to the club? In this case, club service will update their internal state and then issue a REST request, a post request to RMS with the notification. The notification itself is a simple JSON blob that informs RMS what to do with the message. There are a few required fields in that blob. One of them is called resource, which is a REST-like string denoting which component of the client should handle this incoming notification. You can think of the resource as of a routing key that is used by the client to dispatch the notification to the corresponding plugin or subsystem. The next one is version, which is a string that allows us to guard against duplicates. So if the sender service fires few notifications which carry the same version, it is safe to assume for the client that he can ignore it. It also helps with notification reordering, because we use HTTP, requests can actually get reordered on the way to RMS. The next one is a list of player IDs, a list of PUIDs, and that's the list of all players that should receive this notification. In case of batch notifications, for example, whenever the club changes the message of the day, instead of notifying 50 players one by one, club service can actually issue one notification with 50 player IDs on this recipients list. And lastly, we have a short optional payload to deliver, and more about it in a second. So as soon as RMS receives this notification, it will apply internal routing rules and forward that notification to connected client. As a result, client will then go to the club service to fetch the entire state, to figure out what actually happened, why did it receive that notification, and then display a proper toast to the player. As mentioned earlier, RMS can also carry short payloads in the notifications, and they are completely oblivious to RMS. It's just a binary data that is transported from point A to point B, and it can be anything from JSON, base64 blob, XML, or even plain string. Okay, let's dive deep into RMS implementation. As mentioned earlier, RMS is a server-side application. Under the hood, is built by two different tiers, routing and edge. Functionally, routing is responsible for accepting and handling published notifications from external services, like clubs, as well as maintaining a list of all connected players to the platform. On the other hand, edge is responsible for handling player connections, those WebSocket connections I was talking about, and forwarding incoming messages directly to the clients. Both tiers are completely decoupled. We can scale and deploy them independently. For example, in one of our RMS clusters, we have 4 servers that run in the routing tier and around 10 servers, depending on the scale and time of the day, in the edge tier. Their code has their own repository, and we release and version them as completely 2 separate products. Edge tier is a collection of independent servers that do not share anything with each other. Each of the servers is responsible for accepting incoming player connections, authenticating the players by validating the signed JWT tokens, holding the sessions, so holding a persistent TCP connection between player and edge, and also registering them with the routing tier. By registering, I mean issuing a REST request to the routing tier, telling routing tier, hey, player with player ID equals X is connected to me. Forward me any incoming messages, any incoming notifications that are addressed to that player. This tier is typically memory bound because it holds all the player connections in memory. And even though we load tested it pretty extensively, we were able to achieve around 10 million connections on a single server. We decided that we didn't want to put too many eggs in one basket, because losing that one node with 10 million players will result in a disaster. So we decided to cap the number of connections to around 350,000 per box. This tier is also really linearly scalable, and we can increase this tier capacity by simply throwing more servers at it. On the other hand, we have routing tier. This tier is completely different from Edge. It's a cluster of very tightly coupled servers sharing a global routing table, mapping player IDs to the Edge nodes that hold that session. It's also responsible for monitoring health of each of the Edge servers, and also authenticating publishers, accepting incoming notifications, and forwarding them to the Edge tier. This tier is CPU bound, and it's typically much, much smaller than the Edge tier. The routing tier I mentioned a little bit earlier is a simple translation table between player IDs, that's the column on the left, and the Edge nodes, that's the column on the right. This table is globally replicated within the routing cluster and is used whenever there is any incoming notification addressed to the player. We simply perform a lookup in the table and figure out what the Edge node is and forward that message to the Edge node. Let's follow the flow of the published message in the system. First of all, we have a backend service, like clubs, trying to communicate with the players. It sends a REST request, a publish request to RMS. We have a load balancer sitting in the front of the routing servers. This load balancer forwards a notification to any of the existing routing nodes. It can select any because we have that global routing table that is shared across all the servers. One of the routing servers will look up into the routing table, select the Edge node that holds player connection, forward it to that Edge server, which then delivers that to the player using player's WebSocket connection. The entire RMS stack is built using Erlang. Erlang is a functional programming language which comes with a great support for building highly concurrent and distributed systems. Certain language constructs or philosophies, like the one around actor model or the concept of lightweight processes, or even like an excellent standard OTP framework that comes with the language, they allowed us to focus primarily on the core logic of RMS instead of trying to solve scalability issues. The team behind RMS has already built chat and a few other services internally at Riot using this technology. So building RMS was really, really easy, considering we had a lot of other libraries that we used in other projects. If you would like to know more about Erlang, I would highly recommend you reading Learn You Some Erlang book by Fred Hebert. As mentioned earlier, each of the tiers, routing and Edge, are completely separate, and we release them independently. Even though they are two different Erlang releases, we package them in Docker containers, which gives us great service isolation. We can relocate the servers with ease, and also it gives us independence from the underlying OS. We don't have to make any assumptions about availability of the local libraries or installed packages. We have the golden image. We can drop on any server, any cloud provider, and we will be sure it's going to work. Whenever we build a new Docker image, we upload them to AWS container registry. So as you can guess, RMS runs on AWS. However, the code itself does not have any dependencies on the underlying infrastructure. It is completely possible to run RMS on bare metal, your local Mac, or any other cloud provider. For infrastructure automation, we use HashiCorp's Terraform, which is a tool to treat the infrastructure as a code. We store our infrastructure descriptions in a Git repository. We version it. We have history of our infrastructure with all the mutations. And also, we can express it in a very declarative way. This approach allows us to reduce the risk of running into very costly human mistakes whenever someone clicks on the wrong button in the UI, but also gives us, as a bonus, gives us an ability to create ephemeral environments for load testing or for QA within a matter of minutes. We can stand up the entire functional RMS environment with one click of a button. And because RMS is a core piece of Riot infrastructure, as mentioned earlier, used by over 20 different teams, one of our goals when building RMS was that we would like to be the first to know whenever there is any disruption of the service. To do that, we built a battery of automated health checks for simulating publishers and clients. They run every 30 seconds against our infrastructure, and they not only measure correctness of the service, but also verify that the latency is not affected. Whenever we detect any anomalies in the behavior, we have an SNS queue that notifies PagerDuty or Gmail. Okay, let me now try to distill some points that you can use on your own when building similar services. When building and testing distributed systems locally on my Mac at least, I tend to ignore and forget about the fallacies of distributed computing. Those are the set of false assumptions we typically make about our applications. As an example, that the network is reliable. We assume that the split brain syndromes will never happen to us, or that the latency is 0 because I tested it locally using my loopback interface, or that the network is homogeneous and we will not see request reordering. To combat that, to fight this behavior, very early in the development process, we started using a tool called Jepsen. Jepsen is a tool for verification of distributed systems, which allowed us to inject failures and faults into our system. We were able to simulate different types of problems. For example, splitting our routing cluster into 2 different halves, and then after running some additional tests and merging them back, we were able to verify that everything went back to normal and we have consistency in our system. One of the problems that hit us very hard early, when we forgot about that network and the infrastructure doesn't necessarily have to be super reliable, was the example of having too many connections on a single edge server. So whenever one of the instances in AWS failed, which happens from time to time, we lost around 500,000 connections in a single second. All of those players, because of the logic in the client, attempted to reconnect to RMS immediately. So we essentially DDoSed ourselves. Which is fine. I mean, we would like players to be able to connect to RMS at any given time. But the problem was that the load balancer that was sitting between edge and routing tier that was used for registering new sessions was cold. So what happened is 500,000 players were trying to reconnect in the same second, were hammering, and that ELB was trying very hard to warm up, but was failing. And for 5 to 10 minutes, we had 500,000 of players that were completely dark. They were not able to receive any notifications and could not understand what's going on. Like, they were not able to see game notifications or other things. We essentially, at the end of the day, we removed the load balancer entirely from our infrastructure, replaced it with service discovery, and also reduced the number of connections we can have on a single edge server. But that's one of the examples that actually demonstrate how important it is to think about failures when building your systems. Another thing that is really important and dear to my heart is visibility into our systems. We probably collect more statistics than we realistically should, but we try to measure pretty much everything. Things like not only messages published by backend service, but also distribution of different published sizes, the latency within the system, the number of concurrently connected users, publish errors, and so on. It is even more important that with ephemeral containers, with auto-scaling groups, that we used centralized logging and centralized monitoring, because nodes go up and down all the time. And if we only keep the logs and metrics locally on every box, it is more than guaranteed that they're going to be gone within the matter of hours. And we will have no history and no way to really triage, understand what really happened after the fact. We also learned that even though the detailed metrics and monitoring is super cool for developers and maintainers of the system, customers don't really give a shit about it. Right? What they care about is RMS up or down? Do my players actually can receive notifications? And to do that, we decided we need to take a step back, abstract a few things, and really present them with a dashboard that only has two states. Is it green or red? And this dashboard is actually built using those health checks we talked about a few minutes earlier that run against the live system every 30 seconds. Another important thing is a support for dynamic configuration. With such a large number of customers coming in, we had to find a way to fine-tune the system effectively without having to restart the service or go to every single instance around the globe, changing the configs by hand. Our configurations live in a Git repository, and we have a Jenkins job transformer that moves them from that Git repo and publishes them to the centralized configuration server. We call it Configurus. RMS polls that server for changes every 30 seconds as well, and converges dynamically without any need of restart on the new state. It's a perfect thing for us for things like feature toggles. Pretty much every major change we introduce to the system sits behind a feature toggle, which we can turn on and off with a single Git commit globally, and see the change being applied on all the servers around the world in 30 seconds. Also, with a very small team behind RMS, we only have 4 engineers and many internal customers, we had to find a way to avoid becoming a blocker for teams to really triage their problems and adopt our service. We essentially had to build self-service capabilities. We invested a lot in client and publisher SDKs, in documentation examples, and easy-to-use triage tools. As an example here, we have a real-time dashboard that allows publishers to take a sneak peek into what's actually being routed right now in the system. The dashboard allows us to sample the traffic that's en route and display it to the publishers. So whenever they see a problem, they can immediately go and see, oh, is there anything that's actually being processed? Is there anything that is maybe parsed incorrectly? And that way they can at least help themselves first before they come to us for physical help. We intentionally block teams only on creating new accounts, and that's primarily to understand our publisher use cases, needs, and also to establish the relationship between the RMS owners and the customers. Another thing I'm really passionate about is the capacity planning. We load test the entire system to understand its limits, to establish the baseline, and also identify all the bottlenecks. For global centralized service like RMS, we also had to make sure that we have no downtime upgrade capabilities, and we can do it even during the peak hours. During the load test, it was really important for us that we also were able to shut the entire system down and bring it up, even though we had over 10 million players trying to hammer and get back in. That allowed us to simulate and be prepared for any sort of massive failures of our infrastructure, and giving us that assurance that we can bring back the system online, even if it's peak hours and we have so many players trying to reconnect. Question to you. So this is a graph of our concurrent connections to the service, and around the 3rd of May, we experienced some weird behavior. Does any one of you have any idea what it might be? So what happened is, out of a sudden, within a few hours, we essentially doubled our connection counts. The team was like super excited. I was like, fuck yeah, we just doubled the CCU. We established new records, chilling champagne, going to party. Super cool, right? Big numbers. It turned out that actually that was a patch day, and the client got patched, and we ended up with actually, instead of one concurrent connection, we had 2 concurrent connections going to RMS. Yeah, pretty bad. So we had 2 options here. We could either release a hotfix to the client, which would trigger the full rebuild process, retros and everything else, player pain, because players will have to patch the client and log out and log back in, do everything like that. Or we just use the capabilities of our autoscaling groups and resize the system to handle the double of the load. It turned out that not a single page was issued within those 2 weeks, and because we load tested the system to probably 10x of its current capacity, we didn't have to act at all. We just waited for 2 more weeks. That's the date of May 15th, when the new client got released after two weeks, and the connection count dropped back to the original number. Okay, cool. So what's next? Just to wrap up, I wanted to share a few roadmap plans for RMS. First thing is obviously widening the adoption of the service. We would like to have more teams internally to use RMS, pushing even more data through the service. Next thing we are considering about is support for topic-based routing. So instead of addressing individual players, we would be able to say, okay, deliver this message to all players in Germany, or deliver this message to all players using Mac or Windows. And finally, we would like to introduce persistence into the system, which would allow publishers to tell us that this message should be delivered, even though player might be offline right now, so we could persist it somewhere and then deliver it next time the player shows up. If you are interested about more details on RMS, we have a tech blog, Engineering Riot Gamescom. There is a blog post on it. And now I can probably take a few questions, but we can probably do it off stage as well, if that's fine.
Which backend do you guys use for the global routing?
The question was, which backend do we use for the global routing table? We use Mnesia. It's a built-in Erlang distributed key value store. We patched it heavily to support the concurrency and dynamic cluster topology, but essentially the 95% of the code is the standard Erlang library code.
How do you maintain those WebSocket connections when you take an extra off and put a new one in?
How do we maintain WebSocket connections? Sorry, what was the second part of the question?
Like if you take an edge node out.
Mm-hmm. Oh, how do we rotate edge servers with persistent TCP connections? So to do that, we have an internal protocol that whenever the edge server is about to shut down, we receive an SNS notification from autoscaling group, and we drain the connections that are established to that specific edge server. Before shutting down the connection, we send a message using internal RMS protocol to the connected client, telling the client to, hey, I'm about to shut down, please open another connection to the service. That allows us to drain, I think, 300,000 connections in like 2 minutes or so. So it's a pretty fast process.
What do you use for your load balancer?
What do we use for our load balancer? It's a standard ELB from AWS. Because it's WebSockets and we use the classic load balancers, it's actually TCP-based, so we cannot use all the goodness coming with ALBs or like HTTP-aware load balancers, but it's still pretty good. Cool.
How do you keep the routing table updated when the connections are wrong? So if the table maps a query to an edge node, how do you update that?
Okay, how do we keep the routing table up to date with the connections coming in and going out? So essentially, each edge server is aware of all the connections established to that particular node, and whenever there is new connection which is authenticated and established to the server, we issue a REST call to the routing tier to notify about that change. And the same happens whenever the connection is terminated. So edge server will inform the routing tier that the connection is down, and it should remove that player ID from the table itself.
What if the edge node crashes for some reason?
Yeah, so when the edge node crashes, so the routing tier also maintains health check logic for every edge server, so it has some sort of garbage collection mechanism that allows it to eventually clean up the mess in the routing table. We also have, if the unregistered connection call fails, so we like timeout or whatever, next time routing tries to deliver the message to that ghost session, to the orphan session, it will receive 404 error from the edge server that was supposed to hold that session, and will clean itself up as well. Cool.
So does the routing and the edge servers talk over standard Erlang, or is it?
So the question is, what's the protocol used for communication between edge and routing tiers? That's pure REST over HTTP. We use distributed Erlang protocol for internal cluster communication within routing tier. Those are that's normal Erlang cluster. For communication between tiers is pure REST, which also gives us a possibility to potentially replace technologies used on both sides. So we don't have to use Erlang necessarily on both ends. Cool. Sorry, I couldn't hear a question.
Auto-scaling on the edge tier.
Mm-hmm.
How concerned are you with cost, and what, if any, how do you scale servers up and down with expected demand?
Sure. So the question is about auto-scaling of the edge tier, how concerned we are about the cost, and how do we manage our policies for growing the cluster or shrinking it down. We use two metrics. For that, we use CPU utilization, and also we use the connection count metric. I think CPU comes out of the box for AWS. For connection count, we have to run a daemon that essentially publishes that metric to CloudWatch every minute or so, telling autoscaling group what's the current number of established sessions to that server. We are not super concerned. I mean, we are concerned, we are cost aware, but we are not trying to optimize it to its limits. We prefer to play safe on the reliability side and make sure that players have a good experience instead of like trying to save every dollar. But the scaling actions happen probably 2-3 times within a day, so it's not that infrequent. How did we get Erlang distribution working in a Docker? Every single container we have has its own IP address. We also limit the actual range of distribution ports to only, I think, 5 or 6. There are VM settings to specify the upper and lower range. And we also run the containers in the host network mode. So that specifically for the edge tier is important because with the proxy default proxy mode, the proxies will simply get overloaded with like 10 million connections going through them. Okay, I think we are running slowly out of time, but I would love to take any questions off stage. Thank you so much.